Hello my scholars, welcome to my school YouTube channel. My name is Emmanuel. This video will be tackling JAMB CBT past question chemistry for the year 2007. Don't go anywhere, stick around and we'll be right back. You are welcome back to my school YouTube channel. In today's video, we'll be tackling question 26 to 47. Now let's go to question number 26. What is the volume of oxygen required to burn completely 25 cm3 of methane at standard temperature and pressure? I think we need to write a balanced chemical equation first for this reaction. So the reaction is actually between oxygen and methane, because what is the volume of oxygen required to burn complete 45 cm3? So we have methane here, CH4 reacting with oxygen. Okay, of course that reaction is called combustion reaction, because hydrocarbon reacts with oxygen burning in air. We are going to have carbon dioxide, which is CO2 plus what? H2O. Usually when there is combustion reaction involves oxygen reacting with hydrocarbon. The products are usually carbon dioxide and H2O for every combustion reaction that involves hydrocarbon. Okay, oxygen reacting with it, whether it is methane, whether it is propane, whether it is hexane, and so on. The product will always be what? CO2 and H2O. You just need to what? Balance the chemical, the reaction stoichiometry. So let's check now. We have carbon 1 here, 1 carbon here, 4 moles of hydrogen, 4 hydrogen here, we have 2 here. Okay, so we can have 2 here. Okay, then we have oxygen here is 2 here, that's 4. Oxygen here is 2, so we have 2 here. I think the equation is balanced now. Okay, so which means that stoichiometrically we have, if you look at the ratio, this is ratio 1:2, so which means 1 mole. Okay, I'll just say ratio 1 here. 1 mole of CH4 will react with 2 moles of what? Oxygen. So in other words, we can say 1 cm3, of course, will be to what? 2 cm3. Okay, so the question says that what is the volume of oxygen required to burn completely 45 cm3? What is the volume of oxygen? So here, volume of oxygen, directly we have that x cm3. Okay, that is required to burn completely 45 cm3 of methane. So methane, we have 45 cm3. So we just have a simple proportion. Okay, so by the time we cross multiply, x will be equal to 2 times 45. Okay, of course x will be equal to 90 cm3. So which means that 45 cm3 will be of methane will be required to burn what? Or 90 cm3 of oxygen will be required to burn completely 45 cm3. Looking at what? This. So which means that if you don't balance this equation, you are going to have a challenge here. So the amount or the volume of oxygen that is needed to burn completely 45 cm3 of methane is 90 cm3. Let's look at the options we have. Option A says 135, 180, 45, and 90. So the correct answer here is option D, 90 cm3. Let's move on to question number 27. How many electrons are in the L shell of 3115? Of course, that's P. If you identify the element, that is phosphorus. Okay, so phosphorus has an atomic number of 15, and then it has a mass number of that. So the question says how many electrons are in the L shell? I think this is just, let's look at the board. In the L shell, the element is P, phosphorus, 31 here and 15 here. Don't forget that electrons are arranged in shells. Okay, when we want to look at the electronic configuration, so we have, and usually it starts from what? From K. The first shell is K. When we say shell, this is what we mean. This is the first shell. Okay, if you want to draw this of the atom, this is second shell. Okay, this is third shell, and so on and so forth. So this first shell that has the maximum number of electrons to be 2 is shell K. That's shell K. That's L, M. Okay, if we have the fourth shell, that will be what? N. Okay, and so on. So the question says that how many electrons are in this? So what we need to consider is what? We're talking about electrons. What we have here is 15, which is actually representing what? The number of protons, which is also equal to what? Number of electrons in a neutral atom. If the atom is neutral, this is neutral because there is no charge here, no positive, no negative charge. So which means this is a neutral atom. So for this neutral atom, phosphorus to be 15, the atomic number is 15. Okay, I will just say this atomic number is equal to 15, which is, of course, we can say atomic number is also the same thing as what? Number of proton. Okay, they are the same thing. Number of proton, okay, which is equal to what? 15. But don't forget that this is a neutral atom because there's no charge here. And what does it say? In a neutral atom, the number of proton is always equal to number of electrons. So which means that number of proton, okay, I will just write NP to show that number of proton must be equal to number of what? Electron in a neutral atom. In a neutral atom. So, and the number of proton was given to be 15. So number of electron will also be what? 15. So in other words, we want to find the number of shells. And then we know that for the first shell, okay, this is 15 now that we want to work with now. For this first shell, we will have 2 because that's the maximum number of electrons that the first shell can take. The second shell maximum number will be 8. Of course, we have the formula 2n raised by 2, where n is what? The number of electrons. Okay, so we have 2 here for the first shell. The maximum number of electrons this one can take is 8. So 2 plus 8 is 10. So if we take 10 away, subtract 10 from 15, we have 5. Okay, so which means the last one will be what? Will be 5. So the question says, how many electrons are in the L shell? So for this first shell, this is the K shell. This one, the second, this is the what? L, KL. Then this is what? M. Okay, and so on. So, but our concern is what? With the L shell. The question says L shell. So how many electrons do we have in the L shell? We have 8 electrons. So let's move on to the screen. Option A says 5. 5 would have been if it were for M. Okay, for the shell M. Okay, it would have been that. But for the yes, for the M shell, but we have to find for the what? L shell. So because of that, the correct answer is option B. On to question number 28. If the electron configuration of an element is 1s2, 2s2, 2p5, how many unpaired electrons are there? Okay, how many unpaired electrons are there? Let's look at the board and see what we have. We have 1s2, 2s2, 2p5. Okay, so according to Hund's rule, okay, Hund's rule states that first, when we are trying to fill each of the orbital, okay, the orbital, each of them will take a single electron first, occupy a single electron first before you begin to double them. You don't find that. So for this first, 1s2. So let's draw here. The orbit should be for this. This should be for this. This should be for 1s2. This will be for this 2s2 here. Okay, then the p. Don't forget that the p orbital, okay, the p shell actually has 3. Okay, it has a maximum number of 6. So we have px subshell, we have px subshell, we have py, and then we have what? Pz. So and each of them will take what? 2, 2. So which means automatically the maximum number of electrons that should occupy the p orbital should be 6. Maximum should be 6 in the p orbital. Okay, but for this element we have 5 here. So nonetheless, we have sub with x, p sub with x, p sub with y, and p sub with y for the what? For the p orbital. So that means we are going to divide. We are going to have about 3 of that. We have 1, 2. Okay, 1, 2, 3. Okay, so which means this is 2p. This is 2px, 2py, 2pz. Of course, this is 2p5. So let's do it now. So this is 1s2. S orbital has maximum of 2. So the 2 can stay here. 1s2, 1. And then 2. For this, we have 2s2, okay? 2s2. So we have to, what we are drawing is actually what? This what? Electron. That's the electrons. This what? Superscript here. That's what represents the electron. So 2s2 now. 2 is what we have here. So we have 1 and 2, okay? Now for this p now, 2p5, we have 5 of that. According to Hund's, we fill singly first. We want to fill 5 here. So we have 1, 2, 3, okay? We are still going to 5. Then we are done with singly now, single filling now. So we continue from what? Doubling now. 1, 2, 3, then we have here 4, and then we have what? 5. Okay, and then when we are trying to draw it, you see that we draw it opposite, in the opposite. The spin is in opposite direction. So we have drawn 5 now. 1, 2, 3, 4, 5. Okay, so we have only one of these now that is unpaired, because the question says that if the electron is that, say how many unpaired electrons are there. So this one is paired, there are 2 paired. So we have only one of this that is what? That is not what? Paired. So we have just what? One what? Electron, unpaired. One unpaired what? Electron. Okay, so let's go back to the screen. Option A says 2, we have 8, we have 1, we have 4. Okay, so the number of unpaired electrons that we have therein is 1. So the correct answer is option C. Now let's move on to question number 29. Which of the following decrease when a given mass of gas is compressed to half its initial volume? Which of them will decrease? Okay, we have atomic radius of each, we have average intermolecular distance, we have frequency of collisions, we have number of molecules present. I think let's just have a diagram. Let's sketch a diagram out to demonstrate this. Okay, let's assume, let's look at the board. Let's assume, let's say this is the container. If we had a syringe, okay, you can use that to explain, but let's say this is a container. Okay, in this container we have, this is a cover here, or like a plunger. Okay, such that you can apply pressure here to push this in and to push it down. Now inside of this container we have gases here. Okay, molecules of gases in this point here. We have molecules of gases all around. Okay, molecules of gases here, all dispersed that way. Now the volume is still in here. Now the question says that what happens, what will decrease when a given mass of gas, which is this, is compressed to half its initial volume. Okay, now compressing it now means that we apply pressure on this point and then we adjust this thing down and compress. So by the time you compress, see what we are going to have? The volume has been compressed, so we no longer have this down. You have moved this down here, you compress it to half. Let's say such like this. Okay, now we still have the molecules of gases. That has not changed, because the molecules of gas, the volume, okay, has been, because it says that decrease when the given mass of gas is compressed. Is compressing means we apply what? Pressure. Okay, to compress it to half what? Its initial volume. We compress it down. Okay, we bring it down. Okay, so we still have this now. So we take each of the options one after the other. Okay, now don't forget that because of this compression, now what happens? The gas molecules we move together. Now they are no longer having distance. So the distance between them, option A says atomic radius of each of them. Atomic radius of each of them. Now when we talk about the atomic radius, we are talking about the radius of the atom. Okay, that will definitely not decrease. It cannot decrease because the atom remains the same. Okay, the radius remains the same, so nothing has changed there. Okay, in the case of what? The atomic radius of the, because when we talk about atomic radius of each of the molecule, let's say this is the atom, for instance, here from here. Okay, this is the center. From this point to this point, that's the radius of this. So if we have another one here, let's say we have another atom here. Okay, another molecule here. From here to here now is another radius. So from here to this point now, okay, can be the what? The distance, the atomic distance, the radius from here for the whole what? For the entire what? Molecule. So this definitely is not going to decrease. Rather, because you have put them apart, it's going to decrease. So option A is not the answer. Option B says average intermolecular distance. Let's look at it together. Now the distance of this to this point now, okay, or from here to this point now. Now because you have compressed this, what happened? The distance, the molecules between the intermolecular distance between the molecules within the atom will also become smaller. So maybe this one was originally here, because you have compressed it, it has moved closer. You can see maybe this one also had moved closer. This has also moved closer. So the average intermolecular distance between each of the molecules or the particles of the gas definitely will be compressed, will also be reduced together, of course. So which means that atomic radius will not reduce. Okay, well, we say reducing? It will not. Okay, intermolecular distance, okay, is it going to decrease? Of course, yes, it's going to what? Decrease, because the distance between each of the molecules that make up that gas, of the particles, will definitely what? Since they are compressed together, the distance from each other will decrease. Option C says frequency of collisions. Well, frequency of collisions, while they were far apart, okay, we discovered that what the frequency of collision, the collision of what? Will be far away also, to be far. But once you compress it, okay, once you apply force, you compress, what happens? The frequency of collisions will also increase. It will not decrease, because now the molecules are closer to themselves, so they can begin to what? To collide with one another in the container in which they are. So the frequency of collision will not, frequency of collision will not decrease, rather is going to what? Is going to increase, okay, because the molecules or the particles of the gas are being brought together, so the tendency for them to collide with one another is very high. And the last one, number of molecules present. Number of molecules present will not change. It's still the same number of molecules that we have in present. It was only the volume that was what? Compressed down to have that. So based on that, option A says atomic radius of each. That is not correct. Option B says average intermolecular distance. Yes, the distance between the molecules will definitely be what? Be decreased, will reduce. So which means option B is correct. Option C says frequency of collision, it will not what? It will not decrease, rather it's going to increase. And number of molecules present will also not decrease. So based on that, the correct answer is option B. Question 30. The elements that belong to the third period of the periodic table are what? Lithium, beryllium, all of this. So of course, if you know your first 20 elements, it is expected, okay, as a science student or chemistry student, to know your first 20 elements. Even if you don't, I will always recommend that you should know your first 30 elements, okay. You know the 30 elements, first 20 elements, so common. Then from 21 to 30 are the first transition elements, okay, because usually most questions, you know, on the periodic table, if you can master them very well, know their properties very well, you'll be able to do it. We have been able to undo this aspect in one of our video lessons, okay, periodic table, and we delve so much into it. So please, you can subscribe to our video lessons in chemistry so that you can have a good in-depth of this aspect. So let's move on to the board now to see. I've drawn out the periodic table for the first 20 elements, okay. In case, of course, there's a mnemonic that is used. If you look at that video lesson, you can go in there, but let me just mention it. In case you are having challenge trying to memorize the first 20 elements, there are different ones by different teachers, okay. So I will just, what I use is, I will just say hello, that's H, hello, let brighter boys come near our flag, never send, that's the sodium, send men away, since people shall come and praise, that's your potassium, captain. But of course the symbol is what we used, okay. I'll say that again. Hello, hello, let brighter boys come near our flag, never send men away, since people shall come and praise captain. The ones you have to take note is this one, send. Now that's your sodium, but because the symbol is Na, so we use that. Then captain, praise is potassium, but because the symbol is K, so we're using that. So the question says that the elements in the period of the periodic, okay, the third periodic table, and you know that these are what? Your groups, okay, group 1, group 2. So the groups are represented what? Vertically, from up, okay, down, from top to the what? To the bottom. So this is group 1, group 2, group 3, group 4, group 5, and so on, to group 0 or to group O, okay. And then we have periods horizontal, period 1. So in period 1, we have hydrogen and helium. Period 2, we have from lithium, beryllium, boron, carbon, nitrogen, and so on to neon. Then from period 3, we have sodium, okay, sodium to magnesium, aluminium to argon, okay. Then period 4, we have potassium here, and then we have what? Calcium here. But the question is particular about what? Period 3, so which is this point now? Period 3, so we are looking at this, okay. So which means we have sodium, we have magnesium, we have aluminium, we have silicon, we have phosphorus, sulfur, chlorine, and then argon, okay. Now option A says lithium, beryllium, aluminium. Lithium, beryllium, of course lithium falls in here. You can see lithium, beryllium, so that is what? Period 2. So which means option A is absolutely wrong. Option B says sodium, potassium, oxygen, chlorine. Sodium, yes, phosphorus, P, yeah, phosphorus, yes, oxygen is not here. Oxygen is in group what? Is in group 6, of course, period 2. So because it's in period 2, option B is what? Is eliminated. Option C says BCNO. That is boron, carbon, nitrogen. Boron, carbon, nitrogen. Of course, that is what? Period 2. So which means option C is also very wrong. Option D says sodium, magnesium. Let's see, sodium, yeah, magnesium, sulfur, here is sulfur, and then we have argon, and here is argon. So which means option D is the correct answer. Let's move on to the screen. Option A, option D, sodium, magnesium, sulfur, and argon. All of these ones are in period 3. So the correct answer is option D. Let's move on to question number 31. A metal X forms 2 bromides with the formula XBr2 and XBr3. What type of bonding exists between X and bromine in the what? In the bromide? Well, since it's the same element that is able to form 2 bromide, you can see that XBr2 and XBr3. So what does that simply tell us? The X remains the same, but it is Br that is having 2 and 3. So which means that before the bonding, this 2 was actually from X, okay? And then in this other case too, this 3 was actually from X. So which means that X has a variable oxidation number. It has a valency of 2 here plus 2 here, and it has a valency of what? Of 3 here. So which means that, in other words, what it means is that that metal actually is what? Is having a variable oxidation number or oxidation state, which is the characteristic of what? Transition what? Elements. Okay, they have variable oxidation number, variable oxidation state. This one has what? Plus 2 and plus 3. Of course, you know the elements that possibly could be that. But already we're told that a metal X. So if it's a metal that is forming, the bonding is between, because we want to find out which type of bonding is actually engaged. So this is a bonding between what? A metal and bromine. And we know that bromine, is it a metal or a non-metal? Yeah, that's a non-metal, okay? In the group 7 elements, okay? Directly after fluorine, chlorine, bromine, okay? That's a non-metal. So the type of bonding that takes place between a metal and a non-metal, usually that involves the transfer of electrons from the metal, okay, to the what? To the what? Non-metal, is what we actually refer to as what? Ionic what? Bonding, or what we call electrovalent bonding, because there is a donor and there is what? An acceptor. The metal is the one donating because it has excess electron in the outermost shell, and then the non-metal is the one that's what? Accepting. So the type of bonding that involves transfer of electrons, okay, transfer of electrons from metals to non-metals is what we call what? Is what we call ionic bonding or electrovalent bonding. So already we know that this is a bonding between metal and non-metal now, and it involves for transfer of electron, and then we see the variable oxidation state here forming bromide with this. So what type of bonding? Option A says ionic bonding. Of course, that is very correct. Option B says metallic bonding. If it's a metallic bonding, it's type of bonding that takes place between what? The molecules, okay, or the particles of an atom. For instance, you can have Na, sodium, Na+, and like that. We have that. That's metallic. So this is not just, because this is bonding between what? Metal and non-metal. So option B is wrong. Option C says dative bonding. Dative bonding is another name we call coordinate covalent bonding, okay? And that type of bonding involves, is the type of bonding that, in fact, we have dealt with this so much in bonding in one of our video lessons too in chemistry. So please, you can subscribe for that so that we can have that. Because of time, we might not go much into it. But one thing you should know about dative bonding is that it involves sharing of what? Electrons, okay, between molecules. Sharing of electrons, but the electron that is being shared now is donated by one of the participating what? Molecules, okay, that is involved in what? In the sharing, okay. In the place of covalent bonding, of course, covalent bonding also is what? Sharing bonding. In fact, involves what? Sharing of electrons, okay. But this sharing of electrons for covalent bonding, the two participating or the participating atoms definitely what? They will donate. This donate, this one donate, both of them will share. That is covalent bonding. But for dative bonding, the lone pair of electrons that will be shared, the other one does not have. So this one will be one that will bring the lone pair of electrons, then both of them will eventually share that. Of course, we can see that for dative bonding, we can see when ammonia reacts with hydrogen ion, okay, to form ammonium salt, okay, that is for dative bonding. For covalent bonding, all the molecules we have H2, we have Cl2, we have CO2, all of them, I mean, they are what? Covalent bonding. So, based on all of the explanation we've made now, this reaction involves a metal and a non-metal reacting together, okay, transfer of electrons from metals to non-metals. The correct answer, the type of bonding is what? Ionic bonding. So, the correct answer is option A, ionic bonding. Do you know you can take practice questions on our simulated JAMB CBT past questions? All you need to do is to click on the link in the description below that takes you to the Myschool website. There you'll be able to download the Myschool mobile app for your Androids and the Myschool software for your laptops and computers. Please go ahead and start practicing. Now let's move on to question number 32. A mixture of petrol and water can be separated through what? Of course, you must understand that petrol and water are two immiscible liquids. When we say immiscible, that's I-M-M-I-S-C-I-B-L-E, it means that when you mix them together, when I say mix together, you can differentiate between them because of their what? Density. You can separate, oh, this is petrol here, this is water, okay? Whether it is water in petrol or petrol in water, whichever, you can be able to distinguish. So both of them are two immiscible liquids. So all you need to do is what? You pour the mixture, transfer it into a separating funnel, okay? We have handled, in fact, it's one of the topics we have handled also in our video lessons in chemistry. So please, separation techniques, okay, you can also subscribe for that. So we just get the separating funnel, okay? You transfer your medium. Let me just show us there. Let's say we have this. At least this looks like the separating funnel. Okay, here we have a tap here, okay, that we can use in honey there. Then we have here to be this okay, so you bring in your what? Your mixture will be here, your petrol and water. Transfer it into this point, okay? Maybe it gets to this point. And then, of course, this place is locked. This tap is locked here, okay? So what you do is, once you transfer into this now, you now what? You shake a bit. When you shake it, just to allow for what? For easy what? Mixing. So when you shake it, allow it to settle. Of course, you can use a clamp, of course, to hold this. Okay, you can use a clamp for your Rito stand to hold this, and then you have what? A container here, maybe a beaker or something. So by the time you shake, you allow it to settle. Once it settles, you now discover that what? There's an interface. We have, okay, between here, we have maybe depending on the one that is more, okay, if it is just water, you have just dispersed in this, you have water above here, and then you have maybe the petrol down here, or you have petrol here, you are depending on the one that is more in it. So all we need now, once it settles like that, then you just open this tap gradually, and then you have what? This one that you have here will run through, then you stop it, and then what you have here will be the other one. So they are immiscible liquids, so you don't need distillation. Let's look at the options. Option A says centrifugation. You can use centrifugation here because they are two immiscible liquids. If you can use centrifugation when we want to maybe separate the components of blood, okay, like we have the serum, you want to separate the plasma, okay, the red blood cell, and then you want to separate. So once you put it, you centrifuge using centrifugation machine, okay, and then what happens to separate? You see the blood, you have see the serum, the plasma, okay, over there. So centrifugation is not actually needed for this. Option B says distillation. Distillation will be useful if we have, you know, miscible liquids, okay, and then we have what? Differences in their what? Based on differences in their what? Boiling point, we'll be able to what? To separate them. So distillation is not actually required here. Option C says the use of separating funnel. Of course, that's what we just showed now. And option D says the use of filter paper. We use filter paper if we have an undissolved solid, okay, inside, okay, and then maybe we want to have salt and sand, okay. You dissolve your salt, and then you have, you know, you add the salt, water into salt, you stir, the salt will dissolve, you get a solution, and then you have the sand. So you use a filter paper, you filter off the residue will be there in the what? In the funnel, then the what? The filtrate will go in, and then you can go. So you can have filtrate and then the residue. So this is actually not applicable. So the correct answer is option C, the use of separating funnel. I believe you are enjoying this content. If yes, please don't forget to click on the like button, hit the subscribe button, and finally tap on the notification bell to keep you informed once we upload our next video. Now let's move on to question number 33. Which of the following represents an aromatic compound? Aromatic compound. Aromatic compound. So what are aromatic compounds first? Now, aromatic compounds are chemical substances, usually, okay? They are chemical substances that have what we call a conjugated planar ring system. When you say something is conjugated, we have an alternating single bond, double bond, single bond, double bond, okay, in a ring form, okay? When we have that, and then it's usually accompanied by what we call delocalized pi electron, okay? We have them present in aromatic compounds. In fact, in a nutshell, let's just say that for simpler terms, aromatic compounds are compounds of benzene, okay? And what? The compounds of benzene are what? Benzene compounds, and then the what? The derivative of what? Of benzene itself. When we talk about benzene, of course, you know that it was brought about by Kekulé that have the structures that. Let's look at the board to see what the benzene ring look like. Of course, it has a molecular formula C6H6. That's your benzene, and when you draw it, you have something like this. Yeah, 1, 2, 3. This, okay. It is conjugated because we have double bond, single bond, double bond, single bond, double bond, single bond. So that's why we say it is what? Conjugated, okay? Double bond is an alternating doubles bond, single bond, double bond, single bond. This is what? An example, or you can also represent it this way. The ring can be anywhere, of course. The double bond can be anywhere, but it is alternating, whichever one that has the first. So you can start from here, double bond, single bond, double bond, single bond, double bond, single. So it is what? Alternating like that, having what? Pi bond. But when the reaction, we can represent it also this way. We just have this here for easy, then you have what? A ring inside of it like that. Of course, all of these ones, anyone can serve as what? The structure of what? Of benzene. Now, when we talk about aromatic compounds that have what? That are benzene is an aromatic compound with other compounds of what? Or derivatives of benzene. For instance, when we talk about phenol, okay? Phenol is an example of aromatic compound. Phenol, we have toluene, okay? Toluene. We talk of naphthalene, okay? We have of naphthalene. We talk of anthracene, and so on and so forth. We have so many of that. We have xylene, okay? Xylene, so many of them. Phenol usually is a benzene ring, okay? We have benzene ring this way, and then we have OH attached to it. That's what phenol is, okay? Toluene, we have a benzene ring with CH3, of course, with a methyl group attached to it. For naphthalene, we have benzene rings like that attached together. We have anthracene. I think we have about 3 of these together, okay? And then we have another one this way, benzene ring. We have xylene. Xylene is just this, and then we have maybe 1 CH3. Then we have so and so on and so forth. So whichever one, all of these compounds usually they have what? Benzene. You can see a benzene ring attached in whichever way. So for this one, it can be C6H5. We want to represent it. Okay, of course, one hydrogen will not be off because the hydrogen that is removed from here, dehydrogenated, the OH comes to replace. So we have OH, okay? Of course, if you look at the option, this is more likely option A, say C6H5. So this is phenol. Then for toluene, you can have C6H5. Then we have CH3 here. That's toluene. Then we have it and so on and so forth. Now let's move back to the screen. So which of the following represents an aromatic compound? We have C6H5OH, okay? This is phenol, okay? Phenol. That's the old name you can call it. This is a benzene, and then we have OH here. So this is aromatic compound. C6H12. This is just your what? This is your hexane, okay? Hexane. This is your hexane, CnH2n. So this is your hexane, C6H2n. This is a C6H. This of course this is an alcohol, okay? That is hexanol. Yes, hexanol, because we have OH here. So we have, this is your what? C6H4. Of course, this one is your alkyne. So we are talking about aromatic compound. They have benzene ring. That is the easiest way to identify them. They have a benzene. So this is C6H5OH. So the correct answer is option A. Now let's move on to question number 34. We have a chemical reaction here. Equation between, this is CH3, CH2, Cl plus KCl to give this and this. Of course, you can see that we know that Cn is actually negatively charged, okay? then K is positively charged. This is Cl is negatively charged. CH3 is what? CH2 is what? Positively charged. Okay. So now in the reaction above, the cyanide is acting as a what? This is the cyanide now. Now this cyanide is negatively charged here. Okay, but it's definitely going to what? To donate an electron. And usually substances, okay, that donate electrons, there are electrons that act as Lewis base, usually are what we call nucleophile, because nucleophile, they have electron that they are going to what? They are going to donate. Yes, it's negatively charged. Cyanide can be said to be a nucleophile because it is negatively charged and it has a lone pair of electrons that is going to what? To give out to what? A positively charged, species. This way, like in this way, we have CH3, CH2 now. So this is positively charged. So it's definitely going to what? To donate electrons to this and form a bond with this CH3, CH2, because this is what? Positive charge. So this can be said to be what? An electrophile. Okay, this one here that is going to receive from this cyanide that has lone pair of electron is definitely going to be the electrophile, while the cyanide, okay, cyanide ion is going to be what? The what? The nucleophile. Okay, nucleophile. So this cyanide is acting as a Lewis base, okay, while this electrophile is acting as a Lewis acid. Of course, you know the definition of what the Lewis acid is and Lewis base. So this cyanide usually now it has the species, okay, it has a lone pair of electron that is going to what? To donate to this positive charge so that it can eventually become what? It can bond together with it, while this electrophile is the one that is what? Accepting, is positively charged, accepting the pair of electron from this what? Cyanide. So it's what we call the electrophile, and this is what we call the nucleophile. So that settles this. So for this hydrophobic, of course, water loving. We don't have any reaction here that we have water, and then we have hydrophilic. That's the one that has to be what? This is water. Hydrophobic is water eating, okay, or lipophilic. Okay, if it is hydrophilic means that it is what? Water loving, or what we call lipophobic. That means fat. If it is water loving, then it will be oil, eating. If it is water and so on. So it is not hydrophobic, it's not hydrophilic, it is not electrophilic, but it is what? Nucleophilic. So cyanide is acting as a nucleophilic. Of course, electrophilic is acting, the CH3, CH2 plus is the one that is acting as what? As electrophile. So that is electrophilic, because the one that is what? Accepting. It also wants to form bond with the cyanide. So the cyanide here, ion here, is acting as a nucleophile, okay, while the CH3. So the question is all about what? Cyanide. So cyanide here is acting as a nucleophilic. So the correct answer is option C. Now on to question number 35. Which of the following compounds is the best possible anti-knock agent for petrol? Anti-knock. Don't forget that an anti-knock agent, of course, as name implies, anti-knock. Okay, it's a substance, the chemical that is added, okay, to our petrol fuel, usually like the gasoline, okay, to improve the fuel rating, okay, what we call the octane, okay, number rating, okay, to actually improve it so that it tries to prevent the engine from knocking. That's why we call it anti-knocking. Okay, and usually if you're familiar, we know that the old one that was used was 2,2,4-trimethyl pentane. That's what used to be because of the what? So the number of branched chain, okay, usually improves the what? The anti-knocking rate. So which means that those hydrocarbons that have so many branching, okay, substituents attaching to it are more possible anti-knock agents for petrol. They are more efficient, okay, compared to the one that are just what? Straight chain, okay. But in this case now we have CH3, CH2. Okay, let's look at the board and draw some of them. Let's see how it looks like. Option A. This is option A. So let's draw the CH3 2 on C. So we have CH3, 2 of CH3 on C. So C, I'll draw out this C first. Okay, then this H is attached to it. We have one H here. Then we have CH3, 2 of CH3. So we have CH3 here. We have what? CH3. So we have drawn out this. Then we have drawn this. So we have it attached to carbon with one hydrogen atom here. And then we have CH3 attached to it. So we have CH3 here. Then we have CH2, one hydrogen here, one hydrogen here, CH3, one hydrogen here, and one hydrogen here. Okay. let's look at this now for option B. We have CH3, we just have this. Instead of just wasting time drawing now, let's just CH3, then we have it to CH2, one hydrogen here, one hydrogen here. We have CH3 attached to carbon and hydrogen. So this carbon has hydrogen attached to it, okay, and CH3 also attached. So we have CH3 here, then we have drawn this, we have C, hydrogen, hydrogen, then we have carbon, hydrogen, hydrogen, then we have CH3, CH2, CH2, then we have CH3, hydrogen, 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 okay. Option C says CH3, we have CH3, okay, attached to CH2, then we have CH3 attached to carbon and hydrogen, so we have carbon here, we have hydrogen attached to it, then we have CH3 here, then we have CH2, hydrogen here, and that's CH2 there, hydrogen here, and then we have CH3, hydrogen, hydrogen, and hydrogen. And the last one here, we have CH3, 3 of methyl attached to carbon. So one carbon here, we have CH3 here, we have CH3 here, we have CH3 here, okay? Then we have CH2, we have C here, hydrogen here, carbon, hydrogen, hydrogen, carbon, hydrogen, hydrogen, hydrogen. So let's name them now, okay? If you look at this, we have one, of course, this is carbon, of course, if you express this is carbon, hydrogen here, and hydrogen here. So we have 1, 2, 3, 4, 5, okay? Of course, so which means the longest chain is what? Is pentane. So we have on carbon 1, carbon 2, we have a methyl group, carbon 3, we have methyl group, okay? So this will be 2, 3 dimethyl, because we have 2 methyl, okay? Dimethyl pentane. Okay, let's go option B. We have okay, we can expand this also, hydrogen here, hydrogen here, hydrogen here. So the longest chain is 1, 2, 3, 4, 5, 6. So 6, that is hexane, okay? We have only one functional group here, only one here, substituent added here on carbon 1, 2, 3, okay, 3. So that is a 3-methyl hexane. Therefore, this one we have the same thing, 1, 2, 3, 4, 5, 6. That is also what? Hexane. Carbon 3, you have another one there, 1, 2, 3 on carbon 3. That is 3-methyl what? Hexane. So the same thing as that. And then we have for this one, we have 1, 2, 3, 4, 1, 2, 3, 4, 5. That is what? Pentane. We have pentane, okay, just like this. But we have a functional group, methyl group, substituent group on carbon 2, okay. So we have the 2 of them on carbon 2. So for this first one, that is carbon 2. So we'll say this is 2, comma. This is another methyl group here, 2. Then we have what? Dimethyl what? Pentane, okay? 2 dimethyl pentane. So if you look at all of these options we have now, remember we are talking about what? The more the branching, the better the octane, yes, rating, number rating, okay? For here now we have 3 methyl branching. We have just one branching here, just one here, okay? For this we have 2 here, we have 2 here. So option let's nullify option B and C. So we have option A and D. So this is we have 2, 3 dimethyl pentane, and then we have 2, 2 dimethyl pentane. Both of them have the same number of branching, but in terms of trying to rate them now, it is accepted and it is found out that it is discovered that the one that has the 2 branching, okay, on the same carbon atom tend to have a better octane number rating than the one that has it in different what? Of course, both of them have the same number of functional group, okay, attached to the same number of substituents, but because these ones are on 2 and 3, why these ones are on 2 and 2? So the branching here on this carbon tend to have more octane rating than this. So because of that, option D is considered to be. Let's look at the screen. Option D, CH33, okay, with this. So this happens to be the correct answer. So the correct answer is option D. Question 36. The hydrocarbon used in the production of styrene is what? Styrene. Styrene is actually gotten from a monomer that is called ethyl benzene. Okay, when we say ethyl benzene is ethylene. So when ethylene, or which is your ethene, react with benzene, okay, what we have is ethyl benzene. So that is the monomer, okay, that is used in forming what? Styrene. Of course, styrene is also a monomer to what we call polystyrene, okay. Of course, on and on that are used in product. So we are saying that styrene is obtained from ethyl benzene, okay? And ethyl benzene is the formation of what? Reaction between ethene or ethylene, okay, and benzene, okay, to form that. So option A says ethine, no. Propyne, no. Ethane, ethene. Ethene is the same thing as what? Ethylene. So the correct answer is option D. Now let's move on to question number 37. How many structural isomers of chlorobutane are possible? How many structural isomers of chlorobutane are possible? When we talk about structural isomers, how many isomers? Okay, different forms in which the compound can exist. Okay, the number of atoms that make up that compound remains the same, but you can change them. You can change the configuration. Okay, maybe carbon CH3 is on one carbon, and then at another time is another one, obeying the rules. Of course, there are rules that must be obeyed. That's structural isomer. If it is geometrical isomer, geometrical isomer has to do with the cis and trans. Okay, the cis, are they attached? Are they arranged? Is it in cis or are they in trans? Okay, that's the geometric. But we are talking about the structural isomer. So we want to draw all the possible isomers we could find from chlorobutane. Please, let's go to the board and let's start up with it. So we have chlorobutane. So the parent name is what? Butane. Okay, so we have 1, 2, that's 4 carbon atom. 1, 2, 3, and then 4. Okay, so which means chlorobutane. So we can have chlorine on 1. We're not told if it is on carbon 1 or 2. So we have H, hydrogen, because it's only one chlorine. So we can change this chlorine again to be on the second carbon atom. This way, 1, 2, 3, 4. The chlorine atom can be here. Okay, so while this one takes the H, hydrogen, and hydrogen. Now we can move this chlorine. If you move it here now for another compound, because like I said, it has rules we must follow. If you put this chlorine here on this point now, okay, yes, if you look at it, you can say, oh, it's on carbon 3. But don't forget, you can also make your counting from this point. So if you put the chlorine here, it becomes carbon 1, carbon 2. So it is still on carbon 2, and you have already drawn carbon 2. So there's no way we can move chlorine to any of this place again. But one thing we can also do again is we can change the position of this CH3 to be on any of these points or any of these points. Let's see what I mean by that. Don't forget, since the number of carbon must not be more than 4. So we have 1, 2, 3. I can decide to add the 4th carbon here instead of having a straight chain, so that this becomes CH3 here. Okay, then here we have hydrogen, and then we have here chlorine can be here, and then even before chlorine comes here, we can have it at chlorine can be here, then hydrogen is here, hydrogen here, hydrogen here, hydrogen here. Yes, so we move the chlorine back to what? On carbon 1, while the CH3 now as another functional group has been added to this. Then we can also move this chlorine. There's possibility that we can have this chlorine here moved to carbon 2, while the CH3 is also on carbon 2. That's another possible isomer we can have. So that will be 1, 2, 3 carbon. Then the 4th carbon is here, 4 CH3 here, and then we have the Cl also on this point. So we have hydrogen here, hydrogen, and hydrogen atom attached here. So let's name them now. Let's see. This is of course carbon 1, 2, 3, 4. So the chlorine is on. So we can say this is 1 chloro 1, 2, 3, 4. 4. That is but. Okay. 1 chlorobutane. Butane. 4 carbon atom is butane. So this is 2 chlorobutane, because the total number of carbon here is 4. So for this now we have chlorine now on 1. So we have 2 functional groups here that are added, different one. Okay, substituent group. This is chloro, and then this is what? Methyl. And then don't forget, the rule says that what? Alphabetically, which one comes first? This is chlorine, which starting with letter C. This is methyl, starting with letter M. So which means chlorine, C comes before M. So we will name this first. So this is carbon 1, carbon 2, carbon 3. So this will be 1 chloro, okay, then 2 methyl Then how many carbon atoms? 1, 2, 3. That's 3. That is propane. Okay, and then let's look at this last one now. This carbon 1, carbon 2, carbon 3. So both of them are on what? And carbon 2. But don't forget C chlorine, M for methyl. So C comes first. So that is 2. So that will be 2 chloro, comma 2 methyl. How many carbon atoms do we have? Straight chain 1, 2, 3. The longest chain is 3. That is propane. Okay, so we've been able to draw 4 possible 1, 2, 3, 4 possible isomerism. The isomer here now, structural isomers now. So let's look at what we have on the screen. Option A says 4, 3, 2, 1. So the correct answer here is option A. There are 4 isomers, structural isomers that we can have for this what? Chlorobutane that are possible that we can have. So the correct answer is option A. On to question 38. The conversion of open chain alkanes into cycloalkanes and aromatic compounds is called what? Option A says cracking. Okay, this is conversion of open chain into that. Cracking has to do with cracking has to do, when we talk about cracking, there is a higher hydrocarbon. Okay, we have higher molecular hydrocarbon now that is cracked, that is broken down into simpler and smaller what? Hydrocarbons. Okay, that is what cracking. Of course, we can have thermocracking. Okay, like thermal cracking when we have use of heat, and then we have catalytic cracking. Okay, but this now is conversion of open chain alkanes, not breaking down of what? A large molecular hydrocarbon into smaller. So it is not option A. Option B say reforming. Yeah, reforming is a very useful and important process in the petroleum industry. Okay, whereby the open chain usually are converted to what? Of course, they are lower. They are converted into the higher, longer branch chain. Okay, cycloalkanes and then aromatic compounds that is used in the. So it is very important in the petroleum industry. So reforming can be said to be the conversion of the open chain. Of course, like we have the open chain alkanes, the longer chain, the longer chain we now convert into what? Into cyclo. Of course, it's no longer clean, into a cyclic alkane. Okay, into aromatic compounds. Okay, and then we have them into higher compounds. So that is what reforming is. So which means that the conversion of these open chain alkanes into cycloalkanes and aromatic compounds is called reforming. Okay, not cracking. Option C says isomerism. Isomerism has to do with, of course, when we have different compounds that are formed. Okay, they are different compounds, but we have them having the same molecular formula. Yes, but different structural formula. When you configure them in space, spatially, their structures are different. Then we have polymerization, has to do with addition or bringing together combination of 2 or more or many chains of monomers, okay, to form polymers. Okay, that is what we call polymerization. So among these options now, the correct answer is option B, reforming. Let's move on to question number 39. Which of the following alkanes has the highest boiling point? Which of the following alkanes has the highest boiling point? Option A says pentane, ethane, propane, methane. Actually, in alkanes, boiling point increases, okay, with increase in the carbon atom that is present there. In other words, we say that boiling point increases with increase in the molecular size, okay, of the particular alkane. This is as a result of the increase in the London dispersion force. When we say London dispersion force, we are talking about the van der Waals forces, okay, of attraction that exist between them. So all we need to do now is we look at, among the options we have, which one has the longest number of carbon atom, okay, that we have. Option A says pentane. Pentane has 5 carbon atoms. That is C5H12. Yeah, that's pentane. Ethane has 2 carbon atoms. This is 5 carbon atom. Of course, this is C5H. 5 times 2 is 10 plus 2, that's 12. Then ethane is C2H. 2 times 2 is 4 plus 2, that's 6. Then propane is C3. Okay, H. 3 times 2 is 6 plus 2, that's 8. And then we have methane, CH4. Okay, among all of these ones now, this one has 5 carbon atoms, 2 carbon atoms, 3 carbon atoms, 1 carbon atom. So which means that the one that has the highest number of carbon atoms has the highest what? Boiling point. So as a result of that, the correct answer is option A. Now let's move on to question number 40. Certain useful waxes are composed mainly of what? The amino acids, glycerols, alkanols, alkanoids. First of all, we must understand what waxes are. Now, waxes are esters of long chain alcohol and fatty acids. Waxes, I'll say that again. Waxes are esters, okay, of long chain alcohol and fatty acids. So when we talk about esters, don't forget that esters are also referred to as what? Alkanoids, because we get them from reaction of alkanoic acid together with what? With alcohol to give us esters and what? And water respectively. So depending on what it is, like you can have ethanoic acid reacting with ethanol to give us ethyl ethanoate and then together with water. So what we have as the alkanoids are actually what we call esters. So in other words, we can say that the useful waxes, okay, since waxes are esters of long chain alcohol, so which means that they are not amino acids, they are forms of alkanoids. So they are not amino acids, they are not glycerols, they are not alkanols, but they are what? Alkanoids. So the correct answer is option D, alkanoids. Let's move on to question number 41. The IUPAC nomenclature of compound CH3, CH2, COO, CH2, CH3 is what? CH3, CH2, COO, CH2, CH3 is what? Let's move on to the board and we try to draw out the structure. Okay, let's see what it is. CH3, CH2, COO, CH2, CH2. So we want to see the IUPAC. Now, when you want to name the IUPAC nomenclature, first of all, we must identify the functional groups that we have in there. Okay, so this can be, we can represent this now. Let's say this is Al, that's an alkyl group. Then we have COO, that is COO, of course, that's a functional group. Then we have CH2CH, so we can have another alkyl group again, CH2CH, which is this. Of course, this is an alkanoid, okay? This is an ester that we have in here. So we want to name this. Now, in naming, first of all, what we start this is what? We start, of course, because it's the COO, so it's going to end with what? OH, okay, because it's an alkanoid. So essentially, that's what this functional group COO will be. So first, to name, this is the first, we have to name this first, okay? Then we'll now name this together, okay? This is going to be the first we name, then we'll now name this as the second one, okay? Together, then we join them together. So in the light of that, so we are going to name this first. This is representing the what? The first one now, which is the Al prime. Now, we have CH2, CH3. Of course, how many carbon atoms do we have there? We have 2 carbon atoms. So that is F, okay? But because it is going to serve as, you know what we call, we have what we call suffix and what? And prefix, okay? In your English language. So suffix means it is coming before, okay? The naming coming before and then after. So because it is coming before, that's the first name we are going to have, is going to carry what we call eth, because this is 2 carbon atoms, so that will be F. So this will be ethyl. Okay, so this is ethyl. Okay, then we now name the second one now RCOO, which is from here, from this point now to this point. Okay. So this point, so we are going to count how many carbon atoms we have. This is carbon 1, carbon 2, carbon 3. Carbon 1, carbon 2, carbon 3. So that is what? That is prop. Okay, 3 carbon atom is prop. Okay, so we have that to be prop, propan. But because we have COO here, which is an alkanoid, shows the presence of alkanoid, so we call that propanoid. Okay, it will be noid. It must add this name here, propanoid. So which is what this is, propanoid. So that's so what we do now is we just join the two of them together. So like I said, we start with this. We start from this. So that should be ethyl propanoid. Okay, ethyl propanoid. So this is the name of this compound. Let's move on to the screen. Option A says propyl propanoate. Propyl propanoate, meaning that they started naming this first, 1 to CH3, CH2. So they mentioned this first, propyl, then they call this propanoate. So which is option A is wrong. Option B says ethyl butanoate, saying that we have 4 carbon atoms after this, and we have just 3. 1, 2, 3. So this is wrong. Option C says ethyl propanoate. Yes, ethyl. This is ethyl. Then we have propane. 1, 2, 3. But because of this noate, so it becomes propanoate. So option C is correct. And option D says methyl butane. This one. So the correct answer is option C, ethyl propanoate. If you have any question bothering you at all on all we have done so far, please feel free to ask your question. All you need to do is to click on the link in the description below that takes you to the Myschool website. There, you'll be able to ask your question and the solutions will be provided within the shortest period of time. Now, let's move on to question number 42. When temporary hard water is boiled for some time in a kettle, the inner surface of the kettle becomes coated with a deposit of what? Of course, when we talk about temporary hard water, don't forget we have 2 types of hard water or hardness of water, temporary hard water and what? Permanent hard water. It is because of the presence of calcium hydrogen triisocarbonate, okay, or what you call bicarbonate, or magnesium hydrogen triisocarbonate, okay, 4, that is present in the water that makes it to have what? Hard water, to have what? Temporary hard water. So that kind of water, if you boil the water, you are going to treat that water from being hard. Then when we talk about hardness of water, don't forget when you wash with soap and then it does not form lather with soap, we say that water is what is hard. Some people, sometimes when you have your bath, if it's hard water, no matter the amount of soap you use, if I to just end up wasting much soap because the water is hard, to form lather, it takes time. Okay, we have also treated that topic, you know, in our video lesson, chemistry video lesson. So you can subscribe to our video lesson to have a good in-depth of that. So talking about temporary hard water now, it was boiled, okay, just to ensure that what the water is treated is healed out of what? Calcium. So what is present? We say it is calcium hydrogen triisocarbonate. Let's look at the board and see what happens there. Calcium hydrogen triisocarbonate, okay. This is what is present, either this or Mg magnesium, okay. It is magnesium and calcium salt that actually that is present that makes the water to be hard temporarily, okay. So all we need to do now is that what we just apply it here. Once we apply it, what happens? Of course, let me clean up this. This is soluble because it is present in the water. You can't see it physically, but once you add it, you heat it, you put it in a kettle, you now have CaCO3, we now have CO2, of course, will be given up. Then we have what? H2O also. You can balance up the equation. Okay, let's see. Calcium 1, hydrogen is 2. Hydrogen is 2 here. Oxygen is that's 3 here. CO2, this is 3. CO3 here already. Then this and this. So the equation is balanced. So this one now is insoluble. So what we have at the end of the day is that this is what we now have what? Around your kettle. When the water is boiled, you have this now in the kettle, CaCO3, because it's soluble. You see it as white cum, okay? Fluorine around kettle. We call it fluorine in kettle. That's what we have here. This is insoluble. This is what is in the water. But once you boil, this is what you have around the kettle. So the question is asking, what do you have around the kettle? The inner surface of the what? Kettle. It is CaCO3. Let's go back to the screen. Option A says calcium tetraozosulfate 6. No. Calcium triisocarbonate 4. Yes, that is your CaCO3. Calcium tetraozosulfate 6 is calcium CaCO4. No, and this will be present in what? In permanent hard water. It is not removed by temporary hard water. Then we have for calcium hydrogen, this is CaCO3, of course. More likely that's what we got as this insoluble. We have calcium hydrogen triisocarbonate. This will be calcium hydrogen triisocarbonate. Let's not waste much time, okay? We have seen what we are looking for already. Option B is calcium triisocarbonate 4, which is CaCO3. That is what was formed in the inner surface of the kettle, okay, when it becomes coated with when the water is boiled. So the correct answer is option B. Do you have better steps or explanation on all we have done so far? Please feel free to share. All you need to do is to go to the comment section, indicate the question number and the answer you would like to share. Now let's move on to question number 43. A supersaturated solution is said to contain what? Now whenever we have a solution that has more, let's move to the board. There's something that's sketched out here. We know that usually solute will react with solvents, okay, to form solution. Of course, solute is your salt, okay, and then the solvent is what is dissolving the solute to find the solution. So whenever we have more solute, okay, that is dissolved more than it can take, okay, in the solution, we tend to have a supersaturated solution. In that point now, we said it is what? An unstable solution. So in that point, what happens? We can have the solute precipitating out, okay, at any moment because it is unstable. But if we have less solute that is dissolved, that more than it can take in that solution, we say we have an unsaturated what? An unsaturated solution, okay. And if we have, the question is saying a supersaturated solution is said to contain, if we have more solute, like in this case now, more solute than it can take, okay, when it is at equilibrium, when it dissolves at equilibrium, at that temperature, we say we have a supersaturated what? Solution. So, but if it is less, if we have less solute than, let's look at the options we have on the screen, okay. Option A says more solute than it can dissolve at that temperature in the presence of undissolved solutes. So no, this will not, of course, it's not going to even be a saturated solution. Option B says as much solute as it can dissolve at, so this is eliminated, as much solute as it can dissolve at that temperature in the presence of undissolved solute. If we have undissolved solutes there, okay, and then it can take as much solute as it can dissolve at that temperature, this is showing that it is what? It is a saturated what? Saturated solution. This is saturated because it still have much solute as it can dissolve, okay, in the presence of what? Undissolved solute. So this option B is what? Talking about a saturated solution. Option C says as much solute as it can dissolve at that what? At that temperature. At that temperature. So at this point, as much solute as it can dissolve at that temperature. This is unsaturated solution because we have as much solute as it can dissolve in the presence of undissolved. We still have undissolved solutes. Okay, if we still have undissolved solutes present in there, that means it is not saturated yet. So which means it is actually what? It is unsaturated hydrocarbon because we still have some of the what? Of the solutes not dissolved. Okay, this it is more than the solvent. So we say this one is what? Unsaturated. But for this, we have as much solute as it can dissolve at that temperature. So of course, this is what? It is a saturated solution. But for this, we have it has more solute than it can dissolve. More solute than it can dissolve at that temperature, especially when it's at its equilibrium. We say this is what? A supersaturated solution. So option D is the correct answer. On to question 44. The presence of nitrogen in air is to slow down what? Presence of nitrogen in the air. Option A says respiration, and of course respiration, we don't even require nitrogen for respiration. So this makes this, of course, combustion. In combustion, yes, nitrogen does not support burning. Yes, so it's going to slow down combustion. So this is correct for this, but for this it's not. So this makes option A to be eliminated. Okay, option B says combustion and corrosion. Yes, combustion, yes. Nitrogen does not support burning, does not support combustion, so it will slow it down. Then corrosion, yes, because nitrogen, yes, acts as an inert gas, yes, so it's not going to support corrosion. Okay, also corrosion will not take place, so it's going to slow down the rate of what? Corrosion here and combustion. So that's correct. Let's see, like option C says corrosion and respiration. Corrosion, yes, nitrogen will slow down the rate of corrosion because it's an inert gas. And then respiration, of course, like we said, we don't require nitrogen for respiration. So this also is eliminated. Respiration here, transpiration for this alone, this element. So the correct answer here is option B, combustion and corrosion. Let's move on to question number 45. A good drying agent should be what? Of course, if something is said to be a drying agent, it should be able to what? To absorb moisture, absorb water, okay? Water content. Option A says deliquescent. Deliquescent salts or substances, usually when you expose them, okay, what they do is they absorb, okay, moisture, they absorb content, they absorb water in the atmosphere, and then they become solution, they turn into solution, of course. So if they absorb moisture, okay, or water from the atmosphere, and then they turn into solution, then that means we can't use them as what? Drying agent, because as they they obtain the water from the atmosphere, once they're exposed, you see them, they turn into solution. Then that means if you use them as drying agent, they will also turn into solution, and then they will still cause the substance they want to dry to become what? Wet again. So option A, of course, that's why we have caustic soda is an example of deliquescent salt. That's what we call sodium hydroxide. If you see pellets of sodium hydroxide, okay, if you open it, expose it to atmosphere, you bring it from the container, what happens after some times? Absorb moisture, and then they turn into solution, and then you can no longer see those pellets again. So the deliquescent will not be good. Effervescent, when we talk about effervescent, it has to do with gases, okay? When let's say you react calcium carbonate with HCl, okay, and then CO2, react an acid with a carbonate, CO2 is always given off. So that CO2 that is given off there is what we call effervescent. When there's evolution of gases, that is effervescent. So this is not a good drying agent, okay? Hygroscopic, yeah, hygroscopic looks like this too, but the difference is hygroscopic, when you expose them, okay, they absorb moisture content, but they don't turn into solution like this one, okay, and then they keep that substance dry, okay. So this is a good drying agent, okay. It should be hygroscopic, because once you expose them, you bring any substance to them, they do what? They absorb moisture. That's why you see some of these ones, these hygroscopic substances, they put them in substances. Some of the things we buy that we like, the shoes, the footwear we buy, the shoes, you see that thing we have inside the paper, they put it inside, that is a silica gel. We call it silica gel, okay. What is the essence of it is to ensure that what? Moisture is what? Is trapped, okay, is absorbed, so that the shoe, the footwear is not there. Microorganism, once there's no moisture, microorganism or yes, will not be able to what? To have the activity fully impaired. So it keeps that shoe, that substance keeps it fresh. So example of hygroscopic substance, silica gel, calcium oxide is another example of hygroscopic substance. In fact, sulfuric acid, H2SO4, conch H2SO4 is also an hygroscopic. It has sense to dehydrate. That's why we talk about dehydration, okay, of ethanol to form ethane, okay. That is what hygroscopic. So hygroscopic substances usually are good drying agents. Option D says efflorescent. And if it's efflorescent is even the opposite. When you expose the substance, it's got to what? Lose the water of what? Of crystallization. So this also is not. So the correct answer here, a good drying agent should be what? Hygroscopic. The correct answer is option C. Now let's move on to question number 46. Smog usually occurs over cities which what? Usually this will occur, we have this smog more in the urban areas, okay, where we have industries, where we have factories, where we have companies, where fossil fuels, okay, are burnt. Talk about the gases, the gasoline, we talk about the crude oil. When you have the fossil fuels usually burnt off, okay, usually it happens in the urban areas where we have gases like sulfur, oxide, that are exposed, that are given off into the atmosphere. Of course, they cause air pollutants, they contaminate the atmosphere of the air. So smoke usually occurs over cities which burn a lot of fossil fuels. Yes, that is correct. Option B says have very few plants. When we have very few plants, we are not going to have those pollutions, okay, taking place around there when they are burning of those fuels, because we have carbon monoxide also present in the atmosphere, so which is poisonous to the air. So it is not few plants are surrounded by water, of course, no, are overpopulated, no. So the correct answer is option A. Smoke usually occurs over cities which burn a lot of fossil fuels. The correct answer is option A. Question 47. What weight of sodium chloride is needed to make 2.0 dm cube of it? 1.5 molarity solution. 1.5 molar solution. We have sodium is 23, chlorine is. Let's move on to the board and let's solve that question. We're told that what weight of sodium chloride, of course, when we talk about weight, we are talking about mass, okay? So I'll just have that. What weight? So we don't know it. Question mark. Is needed to make 2 dm cube. 2 dm cube, of course, you agree with me that that is volume, 2.0 dm cube, okay, of a 1.5 molar solution. So molar, so that means concentration, okay, 1.5 molarity to do that, okay. So we have to find M. Now we know that we try to look at the relationship. We know that we are looking for mass, but there's no relationship directly between mass, volume, and concentration. But we know that concentration and volume will give us number of moles, okay? And then when we get our number of moles, we can get what? Our mass, which means that for number of moles, we need what? We need the molar mass of that salt, which is what? Sodium chloride. So to start with, let's take this. Number of moles will be equal to concentration multiplied by what? Volume. Remember, we would have divided this by 1000 if the volume were given in cm cube. If what we had was 2 cm cube. So the formula will be number of moles equals to CV over 1000. Okay? But since the volume is already in dm cube, there's no point having divided by 1000. So we just have number of moles is equals to concentration times volume. Of course, this is going to be, the concentration is given to be 1.5, okay, multiply that by the volume is given to be 2.0 dm cube. By the time you multiply 2 by 1.5, we have 3, of course, so this is 3 moles, okay, so that's 3 moles. Now we have number of moles to be 3. The question is, we are asked to find what? Mass. So which means we need what? Molar mass, because we know that number of moles is also equal to what? Mass over what? Molar mass. Usually, when we use this relationship, it is when we are dealing with solutions, okay? Let's say aqueous solutions, okay? Number of moles is concentration times volume for solution or liquid or aqueous solution. But when we use this relationship, number of moles equals to mass over molar mass, we are looking at what? Solid substances, okay? Like in this case now, sodium chloride. So which means we need the molar mass of what? Sodium chloride. So we can have molar mass of NaCl, sodium chloride. This one is easy to calculate. We know that sodium is, of course, this is Na plus what? Cl. The number of moles. Sodium is what? 23 plus chlorine is actually 35.5. It is given. Okay, of course, you should also have that on your fingertips. By the time you solve this, we have that is 58.5. Okay, that's going to be the molar mass. Of course, usually is given in gram per mole. Okay, gram per mole. Now, back to this. So, number of moles is equal to mass over molar mass. So, if you cross multiply, mass will be equal to number of moles times what? Molar mass. So which is equal to number of moles, we got it to be 3. So 3 multiplied by the molar mass is actually 58.5. When you multiply 58.5 by 3, we're going to have, that is 175, of course, 0.5 gram. 1.5, because we have, this is mole, this is gram per mole. So mole, we cancel out mole here, so we are left with gram, okay? So 175.5 gram is going to be the mass of that. So let's look at the options we have. Option A says 116 gram. Option B says 175 gram. Of course, what we had was 175.5 gram, but 175 gram is closest to that. Option C says 87 gram. Option D says 58 gram. So because 175 gram is closest to 175.5 gram, so we go with option B. So the correct answer is option B. I believe you enjoyed this content. If yes, please don't forget to click on the like button, hit the subscribe button, and finally tap on the notification bell to keep you informed once we upload our next video.